Our next organic derivative is the alcohols. And for this one, basically these are organic molecules that have what's called a hydroxyl group. You do need to know that term. And the hydroxyl group is OH. So remember, these are organic compounds. These are not bases. They are organic compounds that have an OH group attached to them. Now, this is called a functional group. Okay, so you're going to see that term come up, more so than with the halogens. All right? This is made both organically through the action of bacteria and yeast, but also it can be done in the lab. And so we're going to go through some of the chemical processes for making alcohols, and then how alcohols are also used in what are called elimination reactions. Now, there's a lot of kind of things that I need to discuss in terms of alcohols. The first one is that they are organized as primary, secondary, or tertiary. And you don't really need to know that or identify them for whatever reason, but sometimes they're referred to that, and we've been finding that occasionally on the diploma or on worksheets. So I do want to talk about them. So a primary alcohol, it basically has the hydroxyl group on an end carbon. So if R is going to be basically the hydrocarbon chain, and basically C is a terminal carbon, then the hydroxyl group is going to be on that first one. So that is a primary alcohol. For a secondary alcohol, you basically have that hydroxyl group on the carbon, but that carbon is attached to two hydrocarbon chains. So that's a secondary alcohol. And a tertiary, I'm pretty sure you can kind of relate to what's going to be. So there's my hydroxyl functional group, and it's going to be attached to three hydrocarbon chains. All right, so that's primary, secondary, and tertiary. And I will basically give you or show you examples of those as we go through our naming. So again, a little box here to summarize things. So general formula, R, remember, being our hydrocarbon, our hydroxyl functional group here. And you recognize an alcohol because they end in OL. So you think about methanol and ethanol that you already know. Those are alcohols according to this. So let's take a look at some examples and properties. So you know a lot of these already from examples. Methanol wood alcohol, by the way, this is used, not good for drinking at all. This is used as antifreeze. It's a solvent, and in fact, some of the hand sanitizer was recalled because it was using this type of alcohol. Ethanol is the alcohol that you can actually drink, although it can be produced, like I said, in a chemical process. And it's often used as a solvent. It's used as basically a disinfectant as well. Ethane diol or ethylene glycol used in antifreeze, glycerol used in soap manufacturing, and a couple of other things here. But you have probably been exposed to alcohols as examples more than anything else. Okay, so properties of alcohols. They are liquids at SATP. Okay, so all alcohols are. They have hydrogen bonding, which is why they're liquids at SATP. And because of that, their boiling points are much higher. So remember, anything with hydrogen bonding from Chem 20 has a much higher boiling point because of that. And so what happens with alcohols is they actually are very soluble, which the term for solubility in water is miscible. So alcohols are very soluble in water. However, what happens is as the chains of the alcohol groups get longer, they become less soluble. And what I mean by that is that if I've got a very long chain of carbons and then that hydroxyl group there, what happens is the solubility of the alcohol decreases because this has so much bigger impact on the properties than just the polar hydroxyl group. And the last thing to mention here is that phenols, which are alcohols made from benzene rings, have low solubility, okay, because of that benzene ring. All right, let's go through examples of how to name these. And what happens here is that you basically use the ending OL, and then what you do is you figure out your parent chain, and we're going to do that here. So our parent chain is 3 carbons long, right here. We know that that's propane, right? And so what happens here is that we drop the E and then we change it to an OL. So this would be propanol. However, we do have to indicate where that hydroxyl group is. So this one, I'm going to number it 1, 2, 3. So this is going to be propan. I've dropped the E, and my hydroxyl group is in carbon number 1, 1-ol. So this is propan 1-ol. I know it seems kind of weird to say, but it is that is basically how it's been decided. In the past, they used to put the number in front, so it would be 1-propanol, and it seems easier to say, but when you add branches to that, it becomes a little bit more difficult. By the way, this is a primary alcohol. Okay, the hydroxyl is on the end carbon. So for the second one, same thing. Parent chain is 4 long. I want to give that hydroxyl group the lowest number possible. So this is 4 carbons. That would be butane. I'm going to drop the E, and I'm going to indicate where that hydroxyl group is. So butan, I've dropped the E, and this is 2-ol. By the way, this is a secondary alcohol. Do you see that you've got the carbon that has the hydroxyl has 2 different carbon chains that are attached to it? And our third example here has a branch. So again, I want the parent chain, again, propane, 3 carbons long. It doesn't matter which way I number it, it's going to give me the same thing. My branch is in carbon number 2, so this is 2-methyl. That doesn't change. Okay. And this then becomes not bute, prop. So propan 2-ol. Okay. Now, for anything 2 and less, I don't need the numbers. So methanol and ethanol don't carry a number. But starting with 3 carbons in the alcohols, you do need it, right? It could either be in carbon 1 or carbon 2. All right. And this, by the way, is a tertiary. So do you notice that this carbon that has the hydroxyl has 3 different carbons that are attached to it? Okay, more naming. The next part here is the phenol group, and the alcohol group on the benzene ring. Now, this is called phenol, and it is a bit of an exception. Okay, there is another way of naming alcohols as well that we're not going to go into because you're not required in Chem 30 at all. But this kind of goes to the point that, remember, we use phenol to indicate that it is a branch, right? And this indicates that the alcohol is more important than the benzene ring. And it is. because when you think about it, that alcohol group is going to be more reactive than benzene. Remember, benzene isn't very reactive at all. It's very much like an alkane. So that kind of gives a little bit more precedence to the alcohol group. So that's something that you are going to know. And remember that it's phenol, not phenyl. Okay? All right, here we go. Next little wrinkle here is, what if I've got two alcohol groups, two hydroxyl groups? And this is where there is a little bit of a wrinkle in the name, which is a bit of a pain, but hopefully you'll get it. It's not that bad, but you'll get it. So again, I want to give those hydroxyl groups the lowest number possible. So I'm going to start numbering this from right to left. I hope you can see that I've got a few branches here. And again, I want to list the branches alphabetically and first. So this is going to be, boy, you can't tell where that fluorine is on. It's between 5 and 6. We'll give it to 6. Okay, so this is going to be 6-fluoro. And that's, I'm going to give it to 4. 4-methyl. And then again, for my alcohols, this is going to be hex. Here's the thing. The E is not dropped when you've got two of them, two or more of the hydroxyl group. So instead of dropping the E, I don't. And this is hexane 1,2-diol. Okay? I know. All right. This next one, this is a line structural diagram. Be careful with this. A lot of students think that there's a carbon here and the OH. Nope, this is just showing you that the OH is connected to this carbon. Okay, so be really careful with that. So that's 1, 2, 3, 4. So I've got propane, no other branches, not propane, butane. So this is going to be butane. Don't drop the E because I've got more than one hydroxyl group. 1,2-diol. All right. 7, going the other way. 2,3-dimethyl, butane, 1-ol. So 4 carbons. I've got a basically an alcohol group. I like to write it on the right here because otherwise I have to write the OH opposite. So I tend to write it on the right-hand side of the molecule. So that means that I've got a methyl group here and a methyl group here. And then the rest of these are hydrogens. Cyclopentanol. Remember, for rings, if they have a double bond or just one branch, you are not going to use the number. And then this is 2,2,2-trichloroethane, 1,1-diol. So again, I like to write these on the right-hand side so I can write it as OH instead of HO. And basically, these are going to be all chlorines. And that's just going to be a hydrogen. Next one, 1,1-dimethyl, propan 1-ol. So here I've got a methyl group, another methyl group, and the rest are hydrogens. And here 2-ethyl, 5-ethyl phenol. So benzene ring, that OH is in carbon number 1. So ethyl, oh, I think I meant 5-methyl, by the way. That makes no sense otherwise. 2, 3, 4, 5. Okay, 5-methyl phenol. Okay. All right, so that's naming of alcohols. And again, except for the part where you keep the E when you've got more than one hydroxyl group, the naming is very similar to a double or a triple bond, so it shouldn't be difficult to adjust to that. Okay, so now reactions involving alcohol. The first one that I want to talk over with you is the addition. So how do we make alcohols in the lab? And it's basically done by an addition reaction. So here I'm going to start with ethene. Remember that addition reactions always involve a double or a triple bond. And what I'm going to do to it is simply add water. So what happens here is the hydrogen is added to one carbon in the double bond. The hydroxyl is added to the other. And so what we get is basically the alcohol. We break the double bond and we make the alcohol. And in this case, we've made ethanol. Okay. Now, question, do I have any other product? I hope you can tell me right away that no, I don't. Because, again, we're adding. We're not substituting in, we're adding. All right, so alcohols are made by addition reactions, but alcohols are useful in the lab because they can be used in elimination reactions. So how do we make unsaturated molecules if we need them? And how we do that is, one of the ways is by using alcohol. So what are these elimination reactions? What do they look like? We'll look at alcohol as one way of doing this, but we'll also show you some other ones as a means of getting elimination reactions to occur. So the first thing you need to know is that elimination reactions are exact opposite of addition. What we're going to be doing is we're going to take a saturated hydrocarbon and make it an unsaturated hydrocarbon. So you're going to see that we're going to be forming double or triple bonds. We're just going to focus on double, but you can do both. Now, one of the ways of doing it is, unfortunately, has the name very similar to what we used in the processing of crude oil, which is cracking, but it's basically the removal of hydrogen. And this requires, this is a laborious process, requires a lot of catalysts to get this to happen. And basically what happens is a hydrogen is removed from each carbon. And so what happens is, to make sure that each carbon has 4 bonds, a double bond is formed. Okay, so we started with ethane and ended up with ethene. Now, any other products here? I hope that you see that because I eliminated those 2 hydrogens, I actually produced hydrogen gas as well. We have to account for all of our atoms. Okay? So this process doesn't happen very often, just removing straight up hydrogen. It's a lot easier to do it by having these functional groups to remove them from. And so where we're going to see this and where they're used very often is, here is ethanol. So you can see that here. And here, by using an acid catalyst, it removes the hydroxyl and a hydrogen from another, the other carbon, and you end up with same product as above, ethene. But this happens a lot more easily in the lab. And your other product here is water that you eliminated. All right? There is a third reaction that I'm going to go through with you. This one is a little bit different, but it pops up again and again on diploma exams. So I do want to go over this with you. And so for this one is, we're going to be removing a hydrogen halide. So we're going to go back to that first group, the halogens that we've looked at. So here is basically chloroethane. Now, this one, instead of a catalyst, remember a catalyst just, doesn't get used up in the process. It speeds up the reaction. This one actually needs another reactant. And it's basically, it needs hydroxide or a base. And so what happens is the base removes one of the hydrogens. I'm going to actually draw it in. So it removes one of the hydrogens. And so what happens is that carbon, it now no longer has 4 bonds around it. So it kicks off the chlorine. So the product is, again, ethene. It's kicked off the chlorine. So I have Cl minus, and that hydroxide has combined with the hydrogen to form water. Okay, so that's a little bit of a different one where you need an extra reactant to actually get it to occur. So our next reaction then is an elimination reaction. And this happens where you take a saturated organic compound and you make it into an unsaturated one. The most common ways that this is done is by removing water from an alcohol to form that double bond. But there is another way where you can use a halogen and a base to actually get the double bond to form. You end up having, though, a few extra products that are produced. We also learned about alcohols in terms of how to name them. And remember that their properties are that they are going to be liquids at room temperature. They have higher boiling points because they have hydrogen bonding, but their solubility decreases as their chain increases because the nonpolar part of the molecule becomes larger in comparison to the polar part of the molecule.